Hello everyone. My name is Sarath Balajepalli. I'm a principal engineering manager at Azure Postgres team. Today I will be talking about Postgres partitioning challenges. My talk would be useful for database administrators and database developers. So let's get started. So today I will be talking about Postgres partitioning challenges. So quick intro about me. I'm a principal engineering manager in Azure Postgres team. I have 18 plus years of experience working on Oracle and Postgres databases. Here in Azure Postgres team, I have experience working on diverse customer workloads. This talk is based on the experience that I have working on diverse customer workloads. One hobby of mine, which I like to share, is I like traveling and explore new places. So, so what are we going to talk about today? So, we will talk about basic concepts. What is partitioning? What is the need for that? Then we'll context switch to partition pruning. Then we'll talk about the two partition challenges: the high planning time and lock manager contention. Then common solutions are what we need to take care while creating partitions on the tables. Then we will also talk about what is new that is coming in Postgres 18. So, what is partitioning? Partitioning in Postgres is nothing but a technique where we divide a very large table into smaller chunks, which are called as partitions. Essentially, we are dividing a very big table into smaller chunks, which are called as child tables. And the bigger the table, the parent table, is split into smaller child tables. So, why is partitioning important? What is the need for that? Basically, I can say that we have five real advantages of doing partitioning. One is improved query performance. Second is reduced index overhead. Third one is efficient data management. Fourth one is improved maintenance. Fifth one is improved scalability. So I'll talk about improved query performance and improved maintenance to start with. Improved query performance because when you partition a table, say you have a table of 200 GB in size, and we do five partitions, 40 GB, then we have less smaller chunks, and we have queries running on these small child tables. Then it doesn't have to scan entire 200 GB. It has to only look into the 40 GB. Definitely, the query performance would be better. Improved maintenance, two things I can add. One is we can detach the partitions, and maintaining the tables become easier. There is no need for deletes, so good archival strategies can be built around this. The second one is, since we are having partition tables, which are nothing but smaller chunks of the larger table, the auto vacuum can be efficient because the auto vacuum runs on the child tables or the partitions, and then we can tune the auto vacuum according to the child table need. So that's a very good addition to have. Then enhance scalability. You can always go and add new partitions. So the it provides the scalability option. Definitely, index overhead is another partition improvement. The reason being, you index a table which is 500 GB compared to indexing a table with 40 GB. The index sizes are smaller on the child partitions. Again, the efficiency and performance boost it gives on the smaller tables. So this is primarily the some of the partitioning, why we have to partition and the need for the partition. So what are the different types of partitions we have today? So we have range partition, list partition, and hash partition. Range partition is a method. Basically, we divide by range of values or date. An example is monthly partition, quarterly partition, or a yearly partition. A list partition basically is divided by a list of discrete values. A very good example might be partition by state names, or a product ID. That is a very good example. Hash partition, the third type, where we don't range and list partition necessarily don't is not applicable. Where here we use a hash key. You're using that hash key, data is distributed among the partitions. So, where are these partition tables metadata getting stored? So, there are different catalog tables specifically for partitions. Those are PG partition table, PG partition index, and PG inherits. It stores details about the metadata about the partition table, partition indexes, and parent child relationships. And of course, the usual PG class, PG attribute, PG constraint, and PG indexes are also used, where the column details and constraint details and others related to parent and child tables get stored. So this is more broadly about the metadata tables or catalog tables associated with the partition. So context switching. I'll talk about the setup that I have. Basically, the content that I'm going to show going forward. I have a bunch of screenshots which I have run on a setup. The setup is nothing but a 16 core Azure flexible server running on a PG17 version. I have a schema that uses PG bench schema. Along with that, three tables I've added: sales table, product table, and PG bench test table. That's the table that I've created. The sales table is a partition table on product ID. There are around 5 partitions. It's a list partition table. The PG bench accounts table is a range partition table on AID column of that table. The partitions vary. So the way the setup is made, the PG bench created the database with a scale factor of 500, but I've created 5 or 6 databases. Each database has different partitions, number of partitions on the PG bench account. So database 1 can have 150 partitions. Database 5 can have 10,000 partitions. And I've used all this information to come up with some of the queries and some of the tests or experiments that I've done to show some of the common challenges that we face for the partitioning. So before we switch to anything else, so before for the first topic that I want to touch upon is the pruning. What is meant by pruning? Basically, pruning is nothing but removal of irrelevant partitions from the query execution. So I have a table, say I have 10 partitions in it, and my data is sitting in one particular partition, and I don't need those 9 partitions. So the way PG or optimizer works is that it can remove those 9 partitions which are not needed. That removal of those 9 partitions and getting the data from that one partition is what is called as pruning. So pruning can be of two types: static pruning and dynamic pruning. So static pruning is nothing but PG or optimizer knows at the planning time what to which partition it has to go and get the data for that particular query. So it has a where clause on the partition key. So during the planning time itself, the the partition that the PG has to go is identified. So in this example that you are seeing, we have a sales table that I spoke of. It is list partition on product ID, and then we have a query. That query is running on product ID is equal to 1. Essentially, we are telling the optimizer before at the planning time itself that it has to go and get all the data where the product ID is 1. So the explain output that you see here, explain analyze output, the one that I have marked says sales underscore P1. That is the partition name. So essentially, it has ignored other partitions. This table is has 5 or 6 partitions. It has ignored, and it went to that one partition where data is sitting. So this is static pruning. The second type of pruning is dynamic pruning. In dynamic pruning, we have initial pruning, where the pruning happens at the plan initialization time. So a good example of that is prepared statements. So in this example, what I've highlighted, the initial pruning is happening uh, at the time of initialization. So initial plan is initialization. This you see a subplans here. It says subplans removed is equal to 149. That means during that time itself, optimizer was able to identify that one partition where it has to go and get the data and remove those 149 partitions that are not needed. So this is happening at the plan initialization because the and then the data is removed. So if you see in the diagram, I have subplans have been removed 149, and it went to PG bench accounts 1. That is the partition on which data was sitting, and data has been retrieved. The second type of dynamic pruning is execution pruning. So again, the pruning key partition key values are not known till the plan execution. So nested loop giants can use this kind of pruning. So if we see closely at this query, we have a query, we have a join on PG bench history and PG bench accounts. We know PG bench accounts is a partition table, whereas PG bench history is not. So the way it is working, PG bench history works as an outer table, and it tries to retrieve the data from that one partition in which data is sitting in PG bench accounts, and it uses the nested loop. And we have a primary key on AID column, so index scans happen. So and then it identifies the exact partition and retrieves the data. What is very interesting for us to see here is, even though the explain plan shows all the planning nodes, but if we observe closely, in this table we had five partitions like A1, A2, A3, A4, and A5. But for A1, A2, A3, and A5, it says never executed. That means that was not considered at all. It's only the A4 that was considered and data has been retrieved. So this is execution pruning, where it is able to identify basically through this nested loops. It is able to identify and get the data, which the planning time, the execution time is pretty fast. Moving on, we will talk about the scenarios where pruning doesn't happen. There are three scenarios where pruning doesn't happen. The first one is where queries don't have any where clause, and I'm running a query on a partition table. Second one is queries that use the join condition, like we have seen, but the nested loop person is not possible on those. And the partition key is the partition. We don't know the partition till the plan execution time. The third one is partition key itself is not used, even though we have a where clause, but that is on a separate or a different column on which the partition key that is not, which is not a partition key. So we'll go about with each example what that means. So the first one is the scenario where there is no where clause. So I have a query. So we have this sales table, and I don't have a where clause. This sales table has five partitions, which has been highlighted. And since there is no where clause, and it starts scanning all the partitions when I execute it. So this is when scenario where pruning is not happening. Second scenario, as I said, it does. We don't use a partition key. Instead, we use some other column. So the sales table that we spoke of is partitioned on product ID, but here we are using sales ID. So because of that, the optimizer, if you see what I've highlighted, starts scanning each and every partition that is present, sales P1, P2 till P5, and looks for that one record, sales ID is equal to 1, and tries to retrieve the data from that from that partition. The next one is a join condition. We have a query on sales and product. Product ID is where we have the partition, we are partitioned on. Product table also has a product ID and a product name. I'm trying to retrieve the data related to product 5. But since we don't know the product ID at the planning time, it starts looking into each and every partition for that data, and retrieves the data. So again, no pruning happening. Looking, the optimizer looks into all the partitions. The Before we context switch, I would like to talk about equivalence class, a concept which is central to high planning time scenario, um, because this is what makes one of the shortcomings. I would put it in that way. So what is an equivalence class? Basically, in a join condition like these scenarios where we are seeing, where we have table 1 dot column is equal to table 2 dot column, the equality conditions. These conditions are stored are stored in a equivalence class. So what is the use of this? The optimizer uses these for query optimization, get optimized join operations, and for predicate pushdowns. So this is the usage of it. So optimizer uses it for query optimization. But there are few limitations of this as of today till Postgres 17. The first limitation is the equivalence member. Basically, I have a equality condition, and that is stored in the equivalence class. That member lookup uh, is stored in a flat list, and a linear search happens. Let's imagine this equivalent condition in case of a partition table. What happens is that the parent columns along with the all the child columns are also stored in this equivalence class. So pretty much the equivalence class will have parent columns, child columns, and the data is stored in the flat list, and then a linear search happens whenever optimizer has to come up with joint strategies for optimal query optimization. So this is one drawback. The second drawback is derived clause lookup. That is something whenever a new whenever a new equivalent equality condition is added, it is derived basically. There's a clause lookup on around it. Even that is stored in a flat list, and the way it searches this flat list again is through a linear search. So essentially, what this happens is as the number of partitions increases, the lookups take time, increasing the planning time. So that's where our first partitioning challenge comes, where the planning time is higher when the number of partitions increases. So in the setup that I have, that I spoke of, I did a small test. Again, this is no benchmark. This is just a test in the setup to see how the planning time varies. The quadruply increases as the number of partitions increase. I have a query where I've used PG bench table, and I've used PG bench accounts on the AID column. So at the planning time, at the execution till the execution time, we don't know what is the AID range or what are the AID values. So so uh, pretty much we are looking into all the partitions here. So we see that the number of partitions as it increases, the execution time remains the same, but the planning time increases. So if we see at the bottom left, the yellow one is the execution time, green one is the planning time. The planning time and the execution time are pretty much same, around 500 partitions when we have 500 partitions on PG bench accounts. As the number of partitions increase, when I have 10,000 partitions on PG bench accounts table, the planning time itself takes 10 seconds, whereas the execution time is in milliseconds. So that is the problem that we have because of equivalence class and the lookups that take time for the optimizer to come up with the appropriate joint strategies. So the how the explain plan looks like, again, a nested loop is used. We see that never executed is there, so pruning is happening, and it only goes to that one particular I would say partition where data is present. But the planning time, as I've highlighted here, in case of 5,000 partitions, the planning time is 2 seconds, whereas the execution time is only 30 milliseconds. So this is one challenge we face, over partitioning, leading to more higher planning time. Now moving to the second issue that we get into, that is lock manager contention. So before we talk about lock manager contention, I want to briefly touch upon fast path locks. What are fast path locks in Postgres? These are lightweight locks. Basically, three types of locking: access share, row share, and row exclusive locks fall into this fast path locks. And one of the drawbacks as of today, I can say that, or one of the things that how it works is every backend can have only 16 fast path locks. So what happens if there is a scenario where we need more locks? So this might happen in case of partition tables. So we have a partition table where we don't use a partition key scenario, or where there is no pruning happening, then there is a high likelihood that parent table would be locked. Along with that, every child table would be locked, and then if it's a DML, that means we have an update or a delete that has no, again, partition key added, then it is going to lock even the indexes across all the partitions. So that's where the lock manager contention starts to happen. So lock manager contention is not but nothing but uh, locking is needed for every parent table, along with every child table and the indexes. Uh, and this lock manager contention basically creates a waiting, queuing, and blocking, resulting in increased application time, application latencies, and we will see a lot of LW lock manager wait events. So I've done two tests for lock manager to show the how the lock manager contention behave. One, in the first test, I increased the number of clients. That means we are increasing the concurrency. Higher the concurrency, the lesser the TPS. That's how it happens. And then in the second scenario, we change the number of partitions, but we keep the number of clients, and then we observe what happens. So the first scenario, uh, again, I have taken a query where partition pruning is not happening. We don't use a partition key query, and we use a simple PG bench test and run the against this query, and we observe the and I observed the TPS, how the TPS was behaving, and for 25 clients, for example, we had around 220, 225 milliseconds for two if I have two indexes on the table. And as I increase the number of clients, the TPS reduce like 150, yeah, in the test. Similarly, if I had reduced the number of indexes to two, so we were at 320 to begin with, but it again came down to around 280 as the number of clients increased to 200. Every time we will see in the test, lock manager LW lock, the wait event that I have shown here in this slide was seen, and the contention was pretty high, leading to lower TPS, and it only worsened as the number of as the concurrency increased, and it also consumed additional server resources like CPU. One more test that was done was again the same query, same setup, uh, two indexes, one index on AID, second index on BID, then four indexes. But this time, instead of changing the client was set at 100, the number of partitions increased. So I started with 500 partitions till 2,500 partitions. The TPS, as can be seen, the green one is with four indexes, yellow one is with two indexes. We started around 2,000 to 2,500 when we had around 150 partitions, but that pretty much reduced, the TPS pretty much reduced to 100 to 150 as the number of partitions increased to 2,500. So again, the lock manager contention, the TPS, there's a high pressure, so TPS reduces. We will also see additional system resources being used like CPU in this scenario. So, what are the solutions we have today? So, it's always very important that we do the database design properly. We identify the columns where which can be made as partition keys according to the not only database needs but even the application needs, which is very important. And most of the queries have to use partition pruning. Otherwise, we are going to get into a situation where lock manager contention might happen if it in a very high concurrent environment. So partition pruning has to happen even if there are updates or deletes or any deletes. It is better to put a where clause with the exact partition on which it has to do. If that doesn't happen, then in a very high concurrent environment, we are bound to see lock manager contention. The third one that we could think of is having the number of reducing the number of partitions. As we have seen, as the number of partitions increase, there is a high risk that partition the planning time might increase. It quadruples as we have seen. So many a time, what I have observed is that we don't need that many partitions. Maybe we have 10 years of data, but for example, we have 10 years of data in a table and we do a daily partition, which will create something like 365 into 3, which will create like thousands of partitions. We don't have to go that route. Maybe we don't need 10 years of data. We need only 1 year of data, where we should have a proper archival strategy, remove the data that is not needed in the actual table, keep the data that is needed, then reduce the number of partitions. Maybe doing a daily partition might not be a good idea. Do a quarterly partition or monthly partition. That would reduce the number of partitions in the table, which would ultimately help in reducing the challenge around the planning times that we have. Then the fourth one I would say is unused indexes, if there are any. As we have seen in a high concurrent environment, if the queries don't have a partition pruning happening, then the lock each index will also create an additional lock. So essentially, reducing the indexes, removing the unused indexes, we are saving ourselves from lock manager contentions, reducing some of those. So this the final one is like moving to non-partition tables. So why is this here, you might ask. The reason for that is there might be situations where application simply it's not possible from the application to partition a table according to the application needs. Then better we don't partition the table for the sake of partitioning. It's better in those scenarios to have a proper partition archival strategy to remove the data that is not needed, have proper auto vacuum settings on the table, maybe at the table level, uh, and tune it properly so that the bloat ratio on the table is controlled and it is efficient. So this is another way of looking at things where from the application perspective, it is not possible. It's not possible to have partition pruning. Then this is one option that can be considered. Moving on, so I would like to talk about PG18. What new is coming in PG18? So we have four commits that I've gone through that I would like to highlight related to partitioning. The first one is speed up equivalence member lookup in Planner. So we talked about two things in equivalence class. One is lookup of equivalence member is slow because it's in some sort of a list. It's basically we do a linear search and that slows it down. The second one is derived clause lookup. Derived clause lookup again, we have seen that it's a flat list and the lookup can be slower. So these two commits that I've gone through, the first one, equivalence member. So now these equivalence members are basically added to an array list, and they are also indexed on their LID. So the lookups would be faster. Similarly, for derived clause lookup, basically in scenarios where we have this derived clause lookup happening on flat list now, and linear search happens. There is a now hash table available for the lookups to happen faster. Definitely, these two would help in making the planning time better. These are the two very good commits that have gone. I'll come to fourth and then switch to third. The fourth one is like we briefly talked about fast path locks, where every backend has 16 slots are slots allocated. Going forward from PG18 onwards, max locks per transaction, that's a parameter that controls how many fast path lock slots that can be added at the server level. So that's one good addition that's going on. So that would reduce the contention on LW lock manager contentions. Then the final one I would like to touch upon is like uh, don't lock partitions pruned by initial pruning. So what does that mean? So in scenarios where query plans are cached, especially in prepared statements, today what happens is that if it's on a partition table, every partition, meaning every child table and every along with the parent table is there is a lock on it. So going forward from PG18, what this commit does is basically it doesn't lock the all the partitions till the initial pruning is completed. So after that, we know that which particular partition has to be looked into. Only that particular partition is basically locked. So these four are very good additions, which would help in reducing some of the challenges we are seeing in up till PG17, and very good additions to PG18. That's it about my talk about common challenges in partitioning. Thank you very much. You can reach me on LinkedIn, and thank you all.